Hi everyone. I wanted to make a quick video going over some of these titration problems because your test is already next Thursday, and a lot of people have, just in general, a lot of people have trouble with titrations. It's a little bit of a hard subject and not a lot of time relatively to your other tests, but I will say practice is everything. And as long as you recognize these patterns, looking at practice problems, I really do think that you can do a lot. Um, And to help you guys, I actually made something last year. When I tutored, I made this little chart that basically summarized all of these patterns. And we're going to take a look at that. Hopefully, you guys will be able to use it and basically keep this chart at like the back of your head when you're taking the test. Hopefully, just recognizing the patterns. All right. Well, that being said, let's go ahead and share my screen. Give me 1 second. All right, you guys should be seeing my screen right now. So basically, this is our chart right here. And there are basically three scenarios we're looking at. All right. So either you have a okay, whatever you're titrating with is always going to be a strong base or a strong acid. All right. But whatever compound you have that in a array lab might be unknown, or the thing that you're titrating is either going to be again a weak, or not again, but another acid or base of some kind, a weak acid or weak base, or you have another strong acid or strong base. All right. Um, Now, that takes me to this area right here. Okay, so that's basically the focal point of this chart. And right down here is if they're titrating each other. And that's the easy one, because if they're titrating each other, no matter what, okay, an acid reacts with a base. And if they react with each other, it'll straight up produce water. And those anions, either the anion or the cation that's produced from the acid or base, they're pretty inert, because remember from what we had before, if you have like NaOH and you do like that cross line between, the Na will just fly off, and it's perfectly acceptable to just write that NaOH as OH minus, because in an actual solution, those ions will be separated, aqueous that is. So there's not a lot going on, because strong acid and strong base, no matter what, they're not going to come together. The equilibrium is really, really imbalanced. So if they're titrating themselves, well, whichever one is in most excess will determine the pH. So right here, okay, I have it right here. And remember, you should convert these to moles, because there are some cases molarity is acceptable, but for this we're changing volumes. So moles is the best way to take a look at these ice tables. So if they're titrating themselves, the first thing you should do, all right, draw an ice table, make their moles, because when they give you units, it will be molarities and volume. And you just multiply molarity and volume, you'll get moles. So straight up getting moles. And now you can work with something. So in your initial row of that ice box, you have moles of whatever you're titrating and whatever you're titrating. And then you cross it all out. All right. Okay. If you have like 0.05 moles of a strong acid and 0.05 moles of strong base, well, they'll cancel out. The only product left will be water and whatever spectator ions they produce, and the pH is going to be pretty neutral. However, if you have a little bit excess, again, going back to whichever one is excess, if you have 0.06 moles of strong acid or H3O plus, and then you have 0.05 moles of strong base, then 0. Here, let me draw what I'm trying to do. So if you're looking at your acid right here, and that's usually an H3O plus and then OH. And if you have 0.05 moles and 0.06, 0.05 moles will subtract from itself, because that's its limiting reagent. That'll cross out 0.05, and all you have left is 0.01 moles of H3O plus. And if all your strong bases used up, and those counter ions to your strong acid or strong base are pretty inert, they're not going to be doing anything, then that 0.01 mole left of H3O plus is still significant. And that is what you use. You use that moles, and whatever mole you have of whatever's left over, remember, cumulative volume, because if you add moles of whatever titrant you have, you're changing the volume. So that new volume, and you get molarity. And in our case, we had H3O plus, and it could be excess base, excess OH, and that will be your molarity. And you just do the negative log of whatever molarity you have, and that gives you the respective pH or POH. So strong acid and strong base titrations are the easiest ones because there's only one outcome. So everyone's in excess, that's what we work with. That's our molarity, and we'll find our pH and POH from there. And it's really good to note that for pretty much all of these situations, all right, if we take a look ahead over here, all right, it's either a strong base titrating a weak acid or a strong acid titrating a weak base. There's only 3 scenarios for each of them. And questions, you will see every single type of question on the test. They'll either come like roundabout questions like, all right, if you have like this kind of titration, what's the best indicator? Or they might even trip you up if you're looking at a weak acid, right? If you're looking at weak acid, as we'll see later, you'll get a POH, but they might ask for pH. So it's really helpful or important that you look at these, look at the questions. So first things first, let's start on the left. The left is a little bit easier. A strong acid titrating a weak base. So you have your situation spelled out to you in that word problem, all right? You draw the ice table. That's the first thing you do. Every single one of these, you draw an ice table. So you draw the ice table, okay, and you notice, all right, there's not enough strong acid to titrate the weak base, all right? If there's not enough strong acid to titrate the weak base, there's excess weak base, all right? Well, if there's excess weak base, so in terms of product, reactant plus H2O, there's still your initial part, which is your weak base, right? Because that was an excess. We also have newly made, I flipped the P and the R around, so my bad, please ignore that. But you have excess weak base and newly made weak acid from your strong acid titrating your weak base. So this weak acid is your conjugate acid, right? So at that point, if both are present, then you have a buffer system. And this is really easy. If you have a buffer system, you just use your HH equation, all right? It's gonna be your best friend for this test. And remember, if this is your HH equation, you always have to use pKa. There's no going around it. Same thing with here, even if you're titrating a weak acid, you have to get pKa. So if they give you Kb, you have to convert it to Ka, and then you find the pKa. They will throw it at you. You have to make sure your units line up. That's where a lot of people will mess up on the test. So hopefully not you guys. Next up is if it's just enough. All right, you draw out your ice table. All right, you have an equal amount. You have the same amount of moles of strong acid, H3O plus, and the same amount of moles for your weak acid, whatever you're titrating. So there's no more weak, or for this case, no more weak base, no more strong acid. All right, you have your reactant, weak base, strong acid plus weak base. All right, you have your conjugate acid and then H2O. Well, if these are out of the picture because they're completely reacted, all you have left is conjugate acid. However, you don't stop there because you're thinking, all right, conjugate acid, let me just use that molarity and solve and put in the negative log equation, solve for pH. That's not the case because the conjugate acid will be a weak acid, or at least in our case it is, because it's not going to dissociate completely. It doesn't have the equilibrium constants like that of the strong acids and strong bases you guys will encounter. So you have to do an entirely separate equation, all right? So again, if you have just enough, you just have to do an entirely separate equation. And if this, your separate equation, what's left is conjugate acid. That's the only thing that remains. So your conjugate acid will be right here. All right, you just do a separate equation, conjugate acid reacting with H2O, you'll get H3O plus, whatever weak base that you regenerated. However, the thing to note, remember, if it's a weak, or if your conjugate acid is a weak acid, it's not going to differentiate that much. So your ratio of product to reactant is going to be very small. So if we go back down here, this is just a little scenario from your worksheet that you counter, all right? This is the second one is the one I'm looking at right now. So if we did a titration, and again, we see, all right, you have your weak base being titrated, weak base being titrated, I guess in this case, I guess it was weak acid being titrated, and yet you conjugate base. This conjugate base, if they react completely, this is the only thing that's left. And there's only conjugate base left, and then there's an equilibrium between them. So you have your molarity, and remember, this is a molarity made from your moles and your cumulative volume. You subtract X plus X plus X. This is basic test 2 stuff. However, in every situation for every weak acid, every weak base equilibrium ice table, this X is negligible because of how small your K values are. If they're so minuscule, they're always, your Q value will always be over 400. So you'll always cross that out. So you'll always have X2 0.0667. This 67 being whatever molarity you have, because you have two X's right here, one of your conjugate acid or your regenerated conjugate acid and just OH. And that will give you the concentration of whatever you're looking at. So going back up to here, X2 over weak acid equals Ka. And remember, make sure you're using Ka, because if we're titrating a weak base, we get a conjugate acid, and that conjugate acid ratio product to reactant is referring to as acidity properties. Now let's take a look at this third problem. What if you have too much? All right. Okay. Too much strong acid. You're doing a lot more than what's needed to titrate that weak base. Well, it's kind of simple. All right. If all that's reacted, it's not going to really do much. So whatever excess strong acid you have, whatever moles you have left, so like again, you have your weak base, strong acid. Let's say you had like 0.01, 0.02 minus 0.01 minus 0.01. This crosses out 0.01. That's how much left strong acid you have. It's not more than you need, but that's still a number of moles, and whatever cumulative volume you have. Again, hope you guys see a pattern, always cumulative volume you have from titrating both liquids. That's your molarity of strong acid, and your molarity of strong acid is going to dissociate completely. So this is going to be your molarity of H3O plus. So you stick that molarity of H3O plus into your negative log, you'll get pH. All right. Now, for this area, it was kind of erased. I don't know what I did. I might have accidentally erased it. That's my bad. But right now, we'll just work with what we have. Now let's look at the conjugate side of that. So now you have a strong base like KOH, CaOH2, NaOH, titrating a weak acid like HF. Amines. You'll see strong bases titrating weak acids, and you'll see the exact same situations. The first one, all right, if there's not enough, this is supposed to say not enough strong base, excess weak acid, okay? It's not enough strong base, excess weak acid. Well, all right, if you draw as an icebox, weak acid plus strong base, equilibria, you have conjugate base plus H2O. Well, if you have initially, I don't know why I wrote that, 0.05, 0.04, 04 minus 0.04 plus 0.04, you have 0.01, 0.04. And these are your concentrations, conjugate base and weak acid. And those are the only species left. And if they're conjugate, I might have wrote CB, if they're conjugate acid, or if they're conjugates of each other, it's going to be a buffer system. All right. So again, you used your HH equation. But the reason why this side is a little bit easier is because this side, when you're conjugating a weak acid with a strong base, you always have to make sure you're using the right Ka value, right? And if it's a buffer system, you're using the HH equation, and you always use the pKa for that. All right. So you must use the Ka value, but they might give you Kb. You might do some weird thing, but you always have to use Ka value for these first ones, right? If there's not enough titrant, okay, use Ka, because you will have to use the HH equation. All right. Now let's take a look at scenario 2. What if you put strong base NaOH and put it with weak acid like HF? You have just enough. All right. All of it reacts. Your entire reactant side, reactant plus reactant minus 0.0 whatever, 0.0, whatever, literally, they cross out, you have nothing left, all right, in your reactants, and all you have left is product. Well, what only product can you have? No more strong base, all right, and that spectator ion is not doing anything. You have your weak acid, you regenerate, or not regenerate, you generate its conjugate base, and then you probably have H2O along with other spectator ions, maybe. Your conjugate base is all you have. And again, your conjugate base is going to be pretty weak species. So it's not going to dissociate completely. Your weak base is not going to be your concentration of OH minus. You're going to have to do a separate equation. Again, if there's just enough, all right, whatever remaining species you have to do a separate equation for. And that separate equation will do the exact same thing. Because right here, this value right here, this is the money one. All right. If WB weak base, and normally in your ICW, you have whatever constant molarity of weak base you have minus X, and then you have X, and then X, whatever species you have. Okay. Just product, reactant. Okay. Remember, X is negligible because those K values are going to be very small. So you can just leave the weak base concentration as it is. And this is the format of those equations. All right. X2 over your concentration, your molarity of weak base equals KB. And this is the other thing. You really have to pay attention for this, all right? Weak acid reacts with strong base, you get conjugate base. And that conjugate base, when it dissociates or reassociates, that equilibrium is on that KB, not Ka. And I'm telling you, I'm 90% sure on your test, you will see something that's just enough, and they'll give you Ka, and you had to use Kb. They'll do that. They'll do that to you. They'll do you dirty. It's all right. But the same situation applies. All right. Okay, let's say you're really smart. You got it. Good job. You get that KB in there, and you just solve for X. Well, that X right here, this is our condensed equation, all right? Whatever molarity you have, all right, molarity minus X, X, and then X, you cross, that X is negligible. You solve for X, it erases itself, but that X is your concentration of H3O plus. So, I might have written that wrong, but whatever you have left is going to be your concentration of OH. And that's going to be what you plug into the negative log. That gives you POH. All right. POH. The same thing here. I hope you guys are seeing a trend, all right? If you're titrating with a strong acid, it's pretty easy because it gives you straight up pH right here. pH values are pretty, and this is your pH as well, because Henderson-Hasselbalch is always going to be pH. Just titrating with a strong base. Well, this is also pH, but that's just because of the nature of the equation we use. Well, we have POH and POH right here, and we'll have to subtract in order to find pH. That's an extra step though. But the last step is if you have too much. Once again, too much strong base, there's not that much else to do. If you have too much strong base, you already reacted with all of your weak acid, and all you have left are your strong base species. Well, your strong base species, will dissociate completely. So if your strong base is NaOH, and Na is just a spectator ion that does nothing, then your concentration of NaOH, like 0.5 molarity, is you're gonna use that same, not concentration, but like amount in your new concentration, because whatever excess moles of strong base you have over the new cumulative volume, that's going to be your molarity of OH. All right. That molarity of OH, you plug into here, and that gives you POH. And then again, if they ask you for pH, you'll have to subtract that. You really have to pay attention. So if you have extra time on the test, which I really do pray you do, I would use that entire time double checking, make sure you're using the right Ka, Kb, solving for pH when they're asking for you to solve for pH. Something you really have to pay attention to. Now, I will post another, or maybe even send Dr. Amateus and Dr. Wagner another copy of this where I don't erase that, and it's going to be updated. So hopefully you guys can see an updated copy and use that as you practice more. Okay, but let's take a really quick example right here. Okay, so if you have a weak acid, all right, you're reacting with a strong base, OH. All right. So if it gives you your molarity and your volume, molarity and volume, all right. Well, let's find the moles real quick so we can do some workarounds with our ice table. And we don't have any base. All right. Well, we solve out that this is 0.005 moles and this is 0.001 moles. All right. So if we subtract this, minus 0.001 mole, minus 0.001 mole, this will cancel out. This will be 0.004 mole plus, because this is a reaction, 0.001 mole, 0.001 mole. All right, let's take a look. All right, so if we remember from this, okay, for titrating with a strong base right here, and we're titrating a weak acid and there's not enough, we're going to use that HH equation. And lo and behold, we do. We have this entire reaction, water's out of the picture. We use all the OH, and the only species left are NH4 plus and NH3. And we have moles for both of them. So here, let's move this down real quick so we can make some room for our HH equation. Now for HH equation, you can use moles. It's a good habit to use molarity, but let's just try it out, okay? So pH equals pKa plus log of our base over our acid. Let's break these down. That's our base, 0.001 mole. All right. Our new volume, all right? So we have 0.025 and 0.01. 0.01 plus 0.025 was 0.035. That's our total volume. That's 35 milliliters. 0.035 liters. 0.004 mole all over 0.035 liters. And now, though they do cancel out, again, doesn't help to, or doesn't hurt to check. And unfortunately, I don't have the pKa on me. I don't know where I put down my pKa for my ammonium. I don't know where I put it. I'm gonna make an example. So Dr. Amateus, Dr. Wagner, or another TA, if you guys see this, don't hold me for not knowing this off the top of my head. Let's say it's like 3.5. Okay. So log of 0.001 over 0.004. You find the log of that, and you add it to 3.5, you get your pH. And your Henderson-Hasselbalch, you'll always get your pH. That's the nature of it. And make sure when you're doing that, you add our lovely pKa. All right. So hopefully this helps. If you have any questions, make sure you ask me in the studio, shoot me a message. I'll try my best to answer a bunch of questions. If you ask questions, it really does help you. Right. So let me stop sharing my screen real quick. All right. Good luck, guys.